Chapter 35, Diffraction. Diffraction covers the Fresnel bright spot, diffraction by a single slit, diffraction by a circular aperture, Rayleigh's criteria for resolvability, diffraction by a double slit, diffraction gratings, X-rays, the Fresnel bright spot, diffraction and the wave theory of light. Diffraction of light is not limited to situations of light passing through a narrowing opening, such as a slit or pinhole. It also occurs when light passes an edge, such as the edges of the razor blade in figure. Look at this, and look at this. The Fresnel bright spot. Diffraction finds a ready explanation in the wave theory of light. However, this theory, originally advanced by Huygens and used 123 years later by Young to explain double-slit interference, was very slow in being adapted, largely because it ran counter to Newton's theory that light was a stream of particles. Austin Fresnel was a young military engineer who believed in the wave theory of light, submitted a paper to the French Academy of Sciences, describing his experiments and its wave theory explanations of them. This is the picture Fresnel delivered. Okay. He shined a light through a circle. Okay. And they found this picture. And the blood spot at the center is the last place we're looking for the light. Nothing bears confidence in the theory so much as having one of its unexpected and counterintuitive predictions verified by experiment.
Although light has properties similar to those of waves, the wavelength of light is so small that we seldom notice the wave-like nature of light. This pinpoint light source will allow us to demonstrate that wave-like nature. If we put the light source behind a small sphere and look at the light coming past the sphere, we see a pattern around the edges caused by interference between different waves of light. Notice the bright spot in the center of the sphere, where we would normally expect no light at all.
Diffraction by a single slit. Diffraction by a single slit, locating the minima. We shine a light through a very narrow slit, 0.15 millimeter. We expecting we get a one light at this one, but actually this is the one we saw. This is we have a minimum dark on both sides. In the center is a bright spot. Okay. When we study this one, we see when a source here is shine a light through a slit, and we observe it through that angle at this place. It's not quite convenient for us to study it. So what we would like to is the parallel light shining on the slit, and it deflects parallel light too. So in this way, we put the source on the focus plot of this lens. So after the lens, it becomes parallel, shine into the slit, and then it deflects, and we collect it at this point, at angle theta to the normal force.
This setup consists of a microwave emitter, a microwave receiver, and a bar graph display whose length is
This is a
proportional to
receiver.
the intensity of the microwaves picked up by the receiver. We'll use it to show how a beam of microwaves is diffracted as it passes through a narrow slit. These two metal sheets are attached to the center of the board with a narrow gap between them. If the microwave receiver is swung through the area in front of the gap, the pattern of microwaves is quite wide. If the slit is widened, will the pattern of emerging microwaves become wider or narrower? The pattern narrows as the slit is widened. This slide has a set of narrow single slits which we can use to diffract a laser beam. We'll shine the beam through 3 different slits and observe the pattern on the screen. Here is the arrangement of laser, slit, and screen. Here is the laser spot with no slit in place. Here is the laser after passing through a 0.704 millimeter slit. Here's the laser spot after passing through a slit 0.352 millimeters wide. Here is the laser spot after passing through a slit 0.176 millimeters wide.
We'll shine the beam from this laser through a slit whose width can be varied by turning a screw. Here is the laser spot on the screen when the slit is open wider than the beam. We'll close the slit down part way. The laser spot now appears to spread out slightly. As we continue to narrow the slit, a pattern of bright and dark spots appears on the screen. When the slit is almost closed, the pattern spreads out so far it nearly disappears. As the slit is opened again, the spot narrows, and the pattern of bright and dark spots reappears. Light passing a thin wire is diffracted. We'll use a thin wire and a laser to show the pattern of bright and dark spots caused by the diffraction. Here is the setup of laser, wire, and screen. This is the laser spot on the screen with no wire in the beam. This is the diffraction pattern obtained on the screen when the wire is inserted.
Huygens principle. All points on the wavefront serve as point sources of spherical secondary wavelets. Now, this is a wavelength in sometime t equal to 0, and all points as a source of the secondary spherical wavelets. So the wave spread out. Okay. After delta t, this one, the wave become this wave become this, and after a time t, the new position of the wavefront will be that of a surface tangent to these secondary wavelengths. Now, this is secondary wavelengths, this is a tangent. So Huygens principle allowed us to tell where a given wavefront will be at any time in the future if we know its present position. Intensity in single slit diffraction, qualitatively and quantitatively. We look at this single slit with a diffraction. We observe a point P, which is at angle theta to the central axis. Okay. We divided the single slit by n equal zone. So each zone with width delta x equal to a over n. When the n approached to infinity, the delta x approaches 0. And delta x is also the separation between two adjacent zones. Based on the Huygens principle, each zone can be treated as a source of secondary wavelets. The diffraction pattern on the viewing screen is formed by superposition of the wavelets from n zones. Now, we look at this one. This is a P, okay? At an arbitrary point P on the viewing screen, with an angle theta to the central axis, and the magnitude of the wavelets from all zones are the same, because the delta x, the width of each zone, are equal. But their phases are different, since they pass through different paths. You look at this, the two lines from neighbor answers, okay? They have paths different. Now look at this. We look at the angle theta, okay? This is the separation, this is lines from the adjacent zone. And the separation delta x equal to a over n approach to infinity, okay? We do a perpendicular line, this one, dashed line. So after that, the two lines have the same path. And the bottom line have extra. So they have path different. This is the green one, the B. The B equal to what? B in this triangle equal to delta x sine theta. So when these two lines reach point of P, they have phase difference. Okay. The phase difference, we convert the path difference into phase difference. We know that 1 lambda distance equal to 2 pi phase change. So delta phi is the path difference of the wavelets from two adjacent zones. Okay, they have both. Now, I will put them together. We wish to derive an expression for the intensity I theta of the pattern as a function of theta. That's the intensity is a function of theta. We find the answer by representing the individual wavelets EI arriving at point P from zone I, called EI, by a phasor, okay, and calculating the resulting phasor amplitude. That's the answer we want to find. Okay, this is we write it, the E electric field at point P angle theta is equal to sigma or EI. This EI is the wavelet electric field arriving from P from zone I. Okay, this is integration actually. From above analysis, at any point P on the viewing screens, two faces from adjacent zones will have a same magnitude, but different phases. And the phase difference is for two adjacent zones is delta phi 2 pi over lambda delta x sine theta, which depends on the location of theta. Okay. Now this is the phase difference between adjacent zones. Okay. If we look at P, which is theta equals 0, that means it's on the central axis. Then we will find delta phi is 0. Okay, they don't have path difference. So when in the central, see each phasor from every zone, they have the same phase. Okay, so they phase put together. This is the E0. Okay, which you can see is the maximum, no more than that one. It's maximum EM. So at the central is always maximum EM. Now, if we deviate, increase the theta, change this angle, we have a delta phi. And then we see this is each adjacent zone have a phase difference. They're the same. Okay? They're the same. This is one. Okay. So we put them together and we find the resultant E. This is the intensity at angle theta, which is smaller than this one. What is this one? This one equal to E maximum, okay? And we will find this E theta. Now, if we increase the theta again, okay, we go further aside. Before we do that, we have new concept. This is the first phaser's phase. This is the last phaser phase. So the change, the difference frame, they call it this phi equal to 2 pi lambda A sine theta. Okay, the phi is the phase difference in radius between the top and bottom rays from the slit from A. So this is A sine theta instead of delta x. Phi is the phase difference between the top and the bottom line from the slit. And we see that if the delta phase further, we increase the theta, delta phi get increased, okay? The phase difference between adjacent phaser increase. And at some point, we can get this one. This one is this point overlap with this one. In other words, this phi is 2 pi. Okay? In this case, E theta is 0. We see nothing. This is a minimum. Okay? And if we further increase the theta, we can have this kind of situation. One round and more. So we can get another maximum. All right? So this explanation. Now we look at this phase. At the center is always maximum because from all sections, they don't have a phase change difference. They are put together, you get a maximum E theta. And then we move a little bit, increase the theta, we find delta phi increase, and we put this phaser together, we get this to E theta. This is smaller than this one. This is the point, okay? And then we increase the delta phi theta, delta phi. So at some point, this is E theta 0. You get this as a first minimum. And then when delta phi again, so we can get another point, look like the smaller maximum, and so on. Let's see, calculate E theta. Now, we do R and R perpendicular to this phaser. This is the E theta we have to calculate, okay? This is a small phaser, and this phi is the phase difference between the top and the bottom line, okay? And we see the E theta from here is 2, this one. This one is R half theta. Now look at this. This is rectangular, this is rectangular. So this phi equal to this phi. This angle is half phi. So E0 is equal to 2. Each one is R sine half phi. Okay? All right. And the phi, this is phi. This angle is phi. This angle phi is equal to E maximum divided by R from this. This is angle is arc divided by radius r. So the r equal to E over phi. We put this r inside, we get E theta equal to 2 E over phi over C. And we put these two to the denominator, we get E0 equal to E maximum sine half phi over half phi. And we let alpha equal to half phi, we can rewrite this one as sine alpha over alpha. Alpha equal to 7 phi. Remember, the intensity is proportional to E squared. The arrow marked E0 corresponds to the amplitude of the wave disturbance and not to the intensity. Intensity proportional to the square. So we can conclusion. The intensity of light when we absorb from angle theta equal to maximum in the center sine alpha over alpha squared. This is the formula, okay? this alpha, you could have phi. You know phi? Phi is a sine theta transferred to 2 pi over lambda. Okay? Now, so we put it inside. So the alpha equal to pi over lambda a sine theta. Okay? Now, I maximum is the greatest value of the intensity, I theta, in the pattern. And it always occurs at the central maximum, where theta equal to 0. Because theta equal to 0, alpha equal to 0, sine alpha or alpha limit equal to 1. Okay? Equal to 1. And then to the minimum. The minimum is sine alpha equal to 0. This is not equal to 0. So we get alpha equal to alpha. This is alpha. Equal to what? Equal to m pi. When it's equal to m pi, sine m pi equal to 0. M could be 1, cannot be 0. 0 is the central, is maximum. Okay, so n may be 1, 2, 3, 4, and so on. This is minimum. Now, look at this formula. We cancel the pi and move the lambda here. When minimum happen, means a sine theta equals m lambda. This is the minimum formula. Okay, m can be 1, 2, 3, 4, not 0, because 0, theta to 0 is always the maximum. Diffraction by single slit. This is the minimum condition. M equal to 1, 2, 3, 4. Okay, and we can find the theta. Okay, find the theta. In a single slit diffraction, dark fringe, this is dark fringe, are produced where the path length difference, a sine theta, between the top and the bottom rays are equal to lambda, 2 lambda, 3 lambda. And at the center where theta equal to 0, it is always maximum. Now, this is a plot from our calculation. Okay, this is the picture we can take. Now, this is central is always maximum. This is the first minimum. We see dark. This is dark. This is the second minimum. Okay. Yeah. The dark is a sine theta equals m lambda. M equal to 1 is the first minimum. Okay. Yeah. This m equal to 2, second minimum. Both sides is symmetry. Okay. If you look at this one, is the narrow slit is narrower, a small it is smaller, then this is the same, 1 lambda, so this should be larger. And that means it's spread. Now, this is spread. Okay. Why the angle is larger, spread. It can be further spread. We can hold something. We first out. Now look at this. If we have a lambda shining almost at the magnitude of the width at the A, here A is about 6.0 lambda, and then we see it's frayed out. If we narrow in the A is 3.0 lambda, you see it flats out. And if A is continue smaller, 1.5 lambda, it gets larger spread out. Example, a slit with A is illuminated by white light, which consists of all wavelengths in visible range. Question A. For what value of A where the first minimum for red line of wavelength lambda 650 nanometer appear at theta equals 15 degree? This is very simple. We just have a formula, we put the number inside. Okay, what do we want? We find the A. We have angle theta 15 degree, and this is the first minimum. So m equal to 1, lambda equals 650 nanometer. So we find A. Very simple. A. It's 2.5 micrometer. Question B. What is the wavelength lambda prime of the light whose first side diffraction maximum is at 15 degrees? Thus coincide with the first minimum for the red line. We have the formula for minimum. The maximum is between two minimum. So maximum formula is not m lambda, that's m plus half. M. So 1.5 is the first side maximum. Central maximum, first minimum. 1 is first minimum. 1.5 is first maximum. 2 is second minimum. 2.5 is second maximum. Yes. So now we know this is a 15. Okay. We know A, so we can find the lambda prime. That's very easy, tedious work. Okay. Yeah. And put A is 2,500 nanometer. Theta is 15. This is 1.5 with the lambda. Okay. Sample. Find the intensities of the first three secondary maxima, the side maxima, in the single slit diffraction pattern of the figure, measured relative to the intensity of the central maximum. We want to find the first side maximum, first maximum, second maximum, third maximum, relative to the central maximum. Now, we know that the formula, the alpha must be n plus half pi. Then we put the formula, we get the maximum. Okay? If this m pi, then it's minimum. So the intensity I m to the I central in this one by formula. Okay? And this one must be 1. So it will be m plus half pi. You can get the 1 maximum. Right? Now let's see this one. We put this one inside. We put m equal to 1, the first maximum. Okay. So the first maximum to the central maximum, we put it is 1 plus half, was 3 over 2 pi. 3 over 2 pi, we can get the percentage. Okay, at 4.5. And the second m equal to 2, this is a 5 pi over 2 over 5 pi over 2, 1.6%. And then put this into 3, this is 7 over 2 pi, get a point. So we see that the secondary successive maximum decreases rapidly in intensity, 1 to 4.5, then to 1.6, then to 0.65. It's very fast. Diffraction by circular aperture. Here we consider diffraction by circular aperture, that is, a circular opening such as circular lens through which light can pass. This is the picture. Okay. This image is not just a point, okay, as the geometric optics treatment would suggest, but a circular disc surrounded by several progressively fainter secondary rings. The analysis of such patterns is complex. It shows, however, that the first minimum for the diffraction pattern of a circular aperture of diameter d is given by sin theta equals 1.22 lambda over d, where lambda is the wavelength, d is the diameter of the ring. Let's check the first minimum of the single slit, which is a sin theta equal to m1. M equal to 1, first minimum. Okay, first minimum, we rewrite it as sin theta equal to 1 lambda over d. Compared to this one, you see, this is the 1, this is 1.22. Okay. The factor 1.22 emerges from the mathematical analysis when we integrate over the elementary radiators into which the circular aperture may be divided.
When laser light passes through the pinhole in aluminum foil onto a screen, the light on the screen is not a simple spot. Instead, we see a pattern of bright and dark circles around a central bright point.
Rayleigh's criteria for resolvability. Resolvability, the fact that the lens images are diffraction patterns, is important when we wish to distinguish two distant point objects whose angular separation is small. Rayleigh's criteria for resolvability is from UK. The angular separation of 2 point sources is such that the central maximum of the diffraction pattern of one source is centered on the first minimum of the diffraction pattern of the other. Look this way. We have 2 separate point sources. We want to separate, now this is angle theta 0, okay? So this one, the maximum is the first minimum of the second one. Or this one, the maximum is overlap with the first minimum of the second forces. Okay. Actually, this angle is the first minimum position. Okay. And we look at it, the pattern on the screen. The screen is local the focal plane. So the difference delta x equal to theta phi. Right? Theta I phi. And we know this one, theta r from Rayleigh's criteria is the first minimum for the aperture diffraction. So theta r should be arcsine 1.22 lambda over d. When the theta is very small, so sine theta approximately equal to theta. So theta r equal to 1.22 lambda over d. Now let's look at the picture. This one, you cannot tell 1 or 2, basically, so this is the 1. And this picture you see, oh, it might be starting 32. And from this picture, you can show this is a 2 object, okay? Now, this is 2 to very close, a little bit separate, this is separate, okay? So this figure shows the visual appearance and corresponding intensity patterns for 2 distant points objects, say stars, with small angular separation.
This black screen has 5 pairs of slits through which light passes from behind. Each successive pair of slits is separated by half the distance of the pair above it. The upper pair of slits can easily be seen as separate, but pairs of slits lower down become progressively more difficult to resolve as separate slits. As the camera moves in, these closer pairs of slits are progressively resolved as separate slits.
Rayleigh's criteria for resolvability is only an approximation because resolvability depends on many factors such as the relative brightness of the sources and their surroundings, turbulence in the air between the sources and the observer, and the functioning of the observer's visual system. However, for the sake of calculations here, we shall take theta 0 equals 1.22 lambda over d as being a precise criteria. If the angular separation theta between the sources is greater than the theta r, we can resolve the sources. If it is less, we cannot. When we wish to use a lens to resolve objects of small angular separation, it is desirable to make the diffraction pattern as small as possible, theta small. Okay. Smaller theta, we need lambda smaller, d is larger. This can be done either by increasing the lens diameter d or by using the light of a short-wave lens. For this reason, ultraviolet light is often used with microscopes because it's shorter wavelengths. It permits finer detail to be examined than visual light. In an electron microscopy, such beams may have an effective wavelength that is 10 to the negative 5 of the wavelength of the visible light. They permit the detailed examination of tiny structures. Sample. Two distant points, we want to separate it. Okay? This is a screen is on the focal plane. So dx equal to f theta I. Okay. A circular converging lens with diameter d 32 millimeter and the focal length f 24 centimeter forms images of a distant point object in the focal plane of the lens. Light of wavelength lambda 550 nanometer is used. Question A. Considering the diffraction by the lens, what angular separation must two distant points objects have to satisfy Rayleigh's criterion? Now, this is the angle. This should be larger than this one, right? Theta Rayleigh. Now, we put the number in sign. Very simple. Lambda is 550 10 to the minus 9 meter. The d is 32 times 10 to the minus 3 meter. So we get answer. The theta, the angle between them much larger than this one. Question B. What is the separation delta x of the centers of the image in the focal plane? Well, that's very simple. Okay, delta x equal to f, so theta. We put theta I, we put f, we get this answer. Okay, get the answer. It's 5.0 micrometer. Diffraction by double slit. Diffraction by double slit. In the double slit experiments, we implicitly assumed that the slits were narrowing compared to the wavelengths of the light illuminating them. That is, A much smaller than lambda. For such narrowing slits, the central maximum of the diffraction pattern of either slit covers the entire viewing screen. Moreover, the interference of the light from the two slits produces bright fringes that all have approximately the same intensity. Uniform distributed and the same intensity. Interference fringes for double slit system. Actually, we see this one when A is approximately equal to lambda. A is not much smaller than lambda. A is approximately equal to lambda. So this one is double slit interference, but not exactly. It has some flavor of single slit diffraction. What is, we see the single slit diffraction when A approaches lambda. This is this one. Okay. Look at it. The first minimum at the same, second minimum at the same location. All right. So this one actually is a combination of double slit interference and a single slit diffraction. Well, look at that. You see this one is a combination of double slit interference and a single slit diffraction. Now this is a single slit diffraction, okay? And this is, you see the double slit interference. This is a double slit interference, the mother, I call it mother. D sine theta equal to m lambda's maximum, okay? And the intensity at angle theta equal to intensity at central maximum intensity cosine squared beta, where beta equal to pi over lambda d sine theta. And this one is single slit diffraction, okay? A sine theta equal to m lambda is the minimum. M equal to 1 is the first minimum here, okay? And here, the intensity at angle theta is central maximum intensity multiplied by sine alpha over alpha squared. Alpha equal to pi over lambda A sine theta, okay? Unfortunately, this one, we require A is much smaller than lambda. In practice, with visible light, however, the condition A much smaller lambda is often not met. So what we have the second generation. It looks like mommy, also looks like daddy, okay? And this is the picture. It's combined with father and mother. Mother is 2 slit interference. Father is 1 slit diffraction. The double slit pattern described by the above equation and displayed in the figure A combines interference and the diffraction in an intimate way. Both are superposition effects in that they result from the combining of waves with different phases at a given point. If the combining waves originating from a finite and usually small number of elementary coherent sources, as in the double slit experiment with A much smaller than lambda, we call the process interference. If the combining waves originating in a single wavefront, as in the single slit experiments, we call the process diffraction. This distinguish between interference and the diffraction, which is somewhat arbitrary and not always adhered to, is convenience one, but we should not forget that both are superposition effects, and usually both are present simultaneously, as in the figure A. You see the sign of 2 slit interference and 1 slit diffraction. This is a 1 slit diffraction, and this is a 2 slit, both diffraction and interference. This is what we really see. We see this is the picture. Okay, now we write its intensity the equal to I central maximum cosine squared beta and sine alpha over alpha 3. Okay, where beta equal to pi over lambda times d sine theta, and alpha equal to pi over lambda a sine theta. This is the diffraction and interference combination. Okay. We look at this one. Beta and alpha. This is a combination. Okay. Now let's see if it is a single slit. What does this mean? Single slit means that separation of 2 slits d equal to 0. The d equal to 0, the beta equal to 0. Beta equal to 0, cosine beta equal to 1. Okay? Okay. So this becomes I theta equal to sine alpha over alpha squared. This is a single slit diffraction. It is double slit interference. What does this mean? This means A is very narrow. A is very narrow. A is 0. A is 0, alpha is 0. Alpha is 0, sine alpha or alpha equal to 1. Okay. So in this case, okay, I theta equal to I maximum. This is This is one, this is the cosine square. This is Young's double slit interference.
When light passes through two thin slits that are closely spaced and onto a screen, it produces an interference pattern of bright and dark spots. These slides have 3 such pairs of slits, each with a different separation. We'll pass a laser beam through each pair to show the resulting interference patterns. Here is the setup of laser, slits, and screen as seen from above. This is the pattern on the screen from a pair of slits separated by 0.62 millimeters. This is the pattern from a pair of slits separated by 0.26 millimeters. Note that the pattern is spread. Here is the pattern from a pair of slits separated by 0.09 millimeters. The pattern has spread even more.
Sample. In a double slit experiment, the wavelength lambda of the light source is 405 nanometer. The split separation D is 19.44 millimeter, and the split width A is 4.050 millimeter. Consider the interference of the light from the 2 slits and also the diffraction of the light through each slit. Okay. This is a combination. Question A. How many bright interference fringes are within the central peak of the diffraction envelope? This is a diffraction envelope symmetry. How many peaks you have? So what we do, now we have to check this one. The first minimum of diffraction, okay? The maximum of the double slit interference is the maximum. Satisfy d sine theta equal to m lambda. And the first minimum of the diffraction is a sine theta equal to x. Now there's the same angle, theta. The theta the same. So we divided this by this one. We cancel out the sine theta. We find that d over a equal to m. In our case, we put the d and a. D is 19.44 nanometer, a is 4.050 nanometer, so m equal to 4.8. What this means? What this means is at this first minimum position, for the double slit interference, we have 4.8 maximum. In other words, 1, 2, 3, 4. The number 5 is outside. At the center, you have a central. So answer our question, how many bright interference fringes are within the central peak of diffraction envelope? We have this 4, other side 4 plus central. So altogether is 4 plus 1 plus 4, 9 bright fringes within the central diffraction maximum. Question B. How many bright fringes are within either of the first side peaks of the diffraction envelope? Now, this is a central envelope, this is the first envelope on both sides. They are symmetry, are the same. What we do, we know this point is m equal to 4.8, and we find this one. Okay. So the maximum of the double slit, okay, is d sine equal to m lambda. And the second minimum is here, okay, a sine theta equal to 2 lambda. We divide these 2, we get m d over a. D over a equal to half m. Okay, so this m equal to 2d over a. We put the number inside, okay, we got m equal to 5, 6, 7, 8, 9. This is because this is 9.6. So inside we have 1, 2, 3, 4, 5. And 5 in the first side peak. And actually 5 is very weak. Okay, 5 is very weak. Sample. What requirements must be met for the central maximum of the envelope of a double slit diffraction pattern to contain exactly 11 bright fringes? Now, we know that for the symmetry reason, central is maximum. If you have 11 bright fringes, that means on the left you have phi, complete phi. On the left you have complete phi. Okay, and this is one. This one should be for double slit minimum. This 1, 2, 3, 4, 5, 6. This is the 6th minimum for the double slit. Okay, so let me see that. For the minimum, this is m plus half. Without half, this is maximum condition. Put half, this is minimum condition. Okay, and you look at this one, single slit diffraction. Here is the first minimum. So this is the first minimum. This theta equal to this theta. It's the sixth minimum of the double slit overlap with the first minimum of single slit. Okay, so we divided each other. The same theta will cancel out. The d over a equal to m plus f. And here we know that one. This m equal to phi, because all completely 11. This is phi 1, phi 11. So m equal to phi. We put this one inside, we get d. Okay, d equal 5.58. Okay, there's a separation between the two slits. It's 5.58. Diffraction gratings. One of the most useful tools in the study of light and of subjects that emitted and absorbed light is the diffraction grating. This is a diffraction grating, somewhat like the double slit arrangement of the figure. This device has a much greater number n of slits, often called rollings, perhaps as many as several thousands per millimeter. An idealized grating consists of only 5 slits. It's 1, 2, 3, 4, 5. It's presented in the figure. When a monochromatic light is sent through the slit, it forms a narrow interference fringes that can be analyzed to determine the wavelength of the light. We first assume that the screen is far enough from the grating that the rays reach at a particular point P on the screen are approximately parallel when they leave the grating. Now, there's a parallel that leave the grating with angle theta. Okay, this is angle theta. This is angle theta. These are equal to angle theta. Okay, then the separation between the two rulings, the delta x equal to d sine theta. D is their separation. Okay. Adjacent lines, they have path different. Delta x, this one. Delta x equal to d sine theta. Then we apply to each pair of adjacent rulings the same reasoning we used for double slit interference. Satisfy d sine theta equal to m. Lambda is the maximum. M can be 0, 1, 2, 3, 4. M equal to 1 is the central maximum. Then have on both sides you have L, M equal to 1, 2, 3, 4. Symmetry. Let's look at 2. This is n equal to 2. Diffraction pattern. This is n equal to 5. Okay. Now they have different numbers of rulings. When n increases, first, the fringes are sharper, narrower. You see this one? A sharper and narrower. Okay. Second, secondary maxima of low intensity appear. In this one, n equal to 5, you have a secondary maximum with low intensity. 3, the position theta maximum, okay, theta minimum are nothing to do with n. They are the same. You look at n2 and 5, the position are the same. Now we look at this one. This one was an intensity plus produced by a diffraction grating with a great many rulings, consists of narrowing peaks. Okay, here labeled with the order number of m. In the center we call the m is 0. Okay, this is 1 symmetry on both sides. 2 and 3 is a narrow peaks. And you look at this, the picture of this diffraction picture. The corresponding bright fringes seen on the screen are called the lines, and they are also labeled with order number m. This is m equal to 0, m equal to 1, m equal to 2 on both sides. This is 0 first, second, the fourth without third. Okay. Order of the visible emission of light from hydrogen. Okay. Notice that the lines, the same lines, okay, to the center, are farther apart at greater angle, large M. Our Gratings' ability to resolve separate lines of different wavelengths depends on the width of the lines. Okay, now here we have half width angle. Okay, the half width angle delta theta half wave of the central line is here. Okay, now we analyze this one like the double slit. The line with, okay, the position here is d sine theta. This is the first minimum. A sine theta equal to m lambda satisfy the minimum. The first minimum, this is the 1. This is A. This is the width of the single reason. Here is ND. Okay. And so this one, delta theta, is equal to approximately equal to 1 lambda over ND. Now, this is the central line. This is the first minimum, so this is called half width angle. This angle actually related to Rayleigh's criterion. If you have another second line, which the maximum must be outside the first minimum of this first one. Okay, so this angle actually is the minimum angle for the criterion. Okay, Rayleigh's criteria to distinguish two lines. In general, the width of the lines maximum is lambda over nd and cosine theta. We have more cosine theta. This theta is defined by the maximum condition. D sine theta equal to m lambda maximum, because theta and this line had half width angle delta theta. We don't prove it.
We'll use these sets of multiple slits on a slide to show the interference of light passing through the slits. This laser will be our light source. Here is the setup of laser, slits, and screen. This is the pattern obtained with a slit spacing of 80 slits per centimeter.
An application of diffraction gratings. We look at this is diffraction grating. We have a light shining so the slit and then go past this lens. Okay, and this is point is on this focus lens. So after this lens, all light are parallel, it's shining on the diffraction grating. So the light will be deflected and we collect it at this angle theta. So when you satisfy d sine theta and lambda, we get a maximum line. this angle you can rotate. And this one, you see, from lambda, the wavelength of light, and theta, we measured, we can define the d, the separation of the grating. Okay? Or from d and theta, we can find the wavelengths. This is a picture of gratifying of cadmium. It has line 1, 2, 3, 4. Okay. As long as you have a combination of this line, then you can prove you have cadmium inside. Gratings, dispersing, and resolving power. Dispersing, to be useful in distinguished wavelengths that are close to each other, as in the grating spectroscope. A grating must spread apart the diffracting lines associated with the various wavelengths. So we give a definition. D is delta theta over delta lambda. This is this difference between the wavelengths of two lines. This is the angle they spread out. This one is larger, is better, right? Now look at this, how we calculate this one. We have this equation, d sine theta equals m lambda. This is the maximum. Okay, so we do the derivative with both sides. We get a d sine cosine d theta m d lambda. Okay, and this was a delta theta delta d theta d lambda. So we found this one, d theta d lambda equal to m divided by d cosine theta. Okay, yeah. So d, we look at the log. To achieve high dispersion d, we must use a grating of small grating spacing d. The smaller this one, the larger this one. Okay, and work in high order as large m. You notice that one, you don't see the end, the number of rollings of this grating. Note that the dispersion does not depend on the number of rollings. The metric system for d is this angle per meter, or radius per meter. Resolving power. To distinguish lines whose wavelengths are close together, the line width should also be as narrow as possible. So we just have defined the resolving power at lambda average over delta lambda. Here, lambda R is the mean wavelength of two emission lines that can barely be recognized as separate, and the delta lambda is the wavelength difference between them. We look at carefully. This definition, all right? We do it. We know this is the maximum. You have to see the line, the d sine theta and lambda. Okay, and we do the derivative on both sides. We get d cosine theta d theta equal to m d lambda. This is a difference, angle different d theta for two lines with different wavelengths. And when we look at the width of this line, each line at this maximum at the half width is lambda over n d cosine theta. We have learned before. Okay? And this is actually related to Rayleigh's criterion. If two lines, they can be distinguished, the angle between them must be larger than this angle, the half width angle. Okay, so with this one equal to this one in order to separate these two lines, and we put this one inside, we get the d cosine theta lambda or n d cosine theta equal to m lambda, and in this way there's a d cosine theta in denominator, d cosine theta in numerator cancel out. So we find r equal to lambda over d delta lambda equal to nm. What is a nice number. We see that. To achieve the high resolution power, we must use the many rulings. Huge larger, the r is larger. Okay? Yeah. Let's look at in the detail. Definition is dispersion, okay, and the resolving power. Okay. We look at two lines. They have the same delta L. One is one frequency, one wavelength, another wavelength. There's another wavelength. We look at this situation. You see the separation? For the same delta lambda, this one separate bigger. So this case, this grating, it has larger d dispersion separate. And this one we calculate is large resolving power. Okay, one power. They narrow like a sling. Okay, so you look at this T. Let's remember, I pick up especially, even though they separate larger, but you cannot distinguish them. Why? Because you see, this maximum is within the first minimum of the second one. So you, based on Rayleigh's discrete, you cannot distinguish them. But this one, even the D is smaller, the separate is smaller, but they are sling. And this one is outside the first minimum of the second one. So you can tell these two lines. So that's why dispersion and resolving power are different things. Okay. The resolving power of a grating must not be confused with its dispersion. Okay, we look at 3 grating. This is grating A has number n 10,000s and D separation 2,540 nanometer. So this nanometer is 10 to the minus 9 plus the thousands. Probably this is about 2 or 3 times 10 to the minus 6 meter. Yeah, and the first maximum is 13.4 degree. D R. The second grating B have number 20,000, double. Okay, and D are the same as A. So the first maximum at the same angle, 13.4. This is D and up. Grating C is number 10,000 as A. So separation different. This is smaller. Okay. So the first maximum, the angle is different, 25.5 degree. Okay. This D and I. And we compare these three, we find out. Okay. A and B, they have the same separation, so they have this is separation the same. So okay, so the D are the same. And grade A and C, okay, they have the same resolving power. They have the same resolving power. Why? Why? Because the number n is the same. And grade C has a high dispersion, okay? Because why? Because the C has the smaller d, so it's high dispersion, okay? And grating B has a high resolution. This is high because it has its larger number n. We look at the picture. This A and B, they have the same dispersion, this angle the same. And the C had the largest dispersion. And grade B, grating B is slim, as it has high resolution power.
We'll shine white light through these 3 diffraction gratings, each with a different spacing of ridges on its surface and onto a screen. This is the pattern from a grating with 3,000 lines per centimeter. Notice the first and second order spectra. Here is the pattern from a grating with 4,000 lines per centimeter. The spectra have moved farther out to the sides. Here is the pattern from a grating with 6,000 lines per centimeter. Now the spectra have spread out so far that only the first order spectra is visible. The colors are now much more intense than before.
Sample. A diffraction grating has 1.26 times 10 to the fourth rulings, uniformly spaced over with air 25.4 millimeter, 1 inch. It is illuminated at normal incidence by yellow light from a sodium vapor lamp. This light contains two closely spaced emission lines, known as the sodium doublet, of wavelengths 589.00 nanometer and 589.59 nanometer, only 0.959 millimeter difference. 8. At what angle does the first order maximum occur on either side of the center of the diffraction pattern? For the wavelengths of 585.00 nanometer. So we see the separation is L over N. L is 24.4 10 to the minus 3 meter. And this is 1.286 times 10 to the 4. So we get a D. It's probably 2 times 10 to the minus 6 meter. Okay, all right. Okay, and we put the equation. The theta, the position of the M. Now we take M equal to 1, it's given. Okay, lambda D, we put the number inside, we get a theta. The theta is about 17 degrees. Remember, this you have to take the unit meter. This take the meter too. Okay, all right. Question B. Using the dispersion of the grating, calculating the angular separation between the two lines in the first order. The D, we know this one. Okay, this definition of dispersion. Okay, and we know that when this calculate is M over D cosine theta. We find the theta. We have D. We have M. It's 1. Okay, the first order. Okay, so we get a D. You put them inside, we get the D. This is a unit is nanometer. Okay, so this is nanometer. This is per nanometer. Remember, not meter. Once we know D, we know delta lambda, we know delta theta. So delta theta equal to D delta lambda. We put this number inside. Okay, we get an angle difference. Okay, very, very tiny. Okay, 3.606 times 10 to the minus 4 radians. Question C. What is the least number of rulings a grating can have and still be able to resolve the sodium doublet in the first order? This is the one we have to use it because R equal to N number. Okay, we know the average wavelength. We know the wavelength difference. We know that's the first order, so we can find N. N needed 999 rulings, about 1,000. Less than this one, you cannot distinguish these two lines. A monochromatic speed of lambda 600 nanometer shines normally on the transmitting plane grating. The second maximum can be observed at an angle of 15 degrees with reference to the normal. What is the separation D of the grating? We know this is the second maximum, so satisfy the D sine theta equal to second to lambda. Theta is 15 degrees, lambda is 600 nanometer, so you can find the D easily. Okay, we'll put a number inside. It's very straightforward. Okay. You have to use the meter as a unit. Okay, so we get D is 4.6 times 10 to the minus 6 meter. Question B. If a light with a wavelength difference delta lambda of 0.02 nanometer from lambda 600 nanometer can be resolved, then what is the least number of rollings in this grating? Well, then that means m equal to 2, the second order. Okay. Now we use this definition, resolving power. Okay. This is delta lambda 0.02, meaning lambda is 600 nanometer. Okay. And this should be equal to nm, m equal to 2. So we can find n. Okay. This n is 15 thousandths. X-rays. X-rays are electromagnetic radiation whose wavelengths are of order of 1 angstrom. 1 angstrom is about 10 to the minus 10 meter. Compare this with a wavelength 550 nanometer, 5.5 times 10 to the minus 7 meter, at the center of the visible spectrum. The standard optical diffraction grating cannot be used to distinguish between the different wavelengths in the X-ray wavelength range. Why? Now check. This is angle the first order for the X-ray. This is the one. This is X-ray 1 10 to the minus 10. This D is around this one. D is around 10 to the minus 6 order as usual. We put this one, we found this theta is so small, you cannot tell it. So what we do, we need to find some grating with D is approximately equal to the wavelengths. Well, where to find it? Where to find it? Let's see how X-ray was emitted. This is the heat, okay, resistance. We apply a current. So it will have a current, it getting heater, and electron inside escape from it. Once it escapes from to the space, there is a huge voltage applied. So this is positive. So the electron will accelerate, hit the positive. Okay, and this is a metal tungsten. And that when electron hit the tungsten, a tungsten will elect X-rays. X-rays are produced when the electron escapes from the heated filament F, are accelerated by potential difference V, this potential V, and strike a metal target T, and the tungsten emitted X-ray. In 1912, it occurs to German physicist Max von Laue that a crystalline solid, which consists of a regular array of atoms, might form a natural three-dimensional diffraction gratings for X-rays. This is sodium chloride crystal. Okay, the idea is that in a crystal such as sodium chloride, a basic unit of atom, we call it unit cell, repeats itself throughout the array. This is a unit cell of sodium chloride, the salt. Okay. In sodium chloride, this is the unit cell. You have 4 sodium ions and 4 chloride ions are associated with. Okay. So this is the picture section of soda crystal, sodium chloride, and identify this basic unit. This is the basic unit. Okay. The basic unit cell is the cubic measuring A0 on each side. And you will have question. You see, there's so many atoms in each unit cell. How come you see only 4 sodium ions and 4 chloride ions? Now, when we analyze, we find this chloride is on the corner. So this atom is shared by 8 unit cells. Because a corner you have 8 shared. And so only 1/8 of this chloride belong to this one. And this chloride on the face, it shares with another one. So only half belong to it. So we put this together, you will find only 4 chloride and 4 sodiums included in this unit cell. This is a microphone call from Germany. Although the procedure of diffraction of X-rays by a crystal is complicated, the maximum turns out to be directed as if the X-ray were reflected by a family of parallel reflecting plates, okay, or we call crystal planes, that extend so the atom, you have atom on that one, within the crystal, and that contains regular arrays of the atom. The X-rays are not actually reflected. We use these frictional planes only to simplify the analysis of the actual diffraction process. Bragg's law. We define a theta, are defined relative to the surface of the reflecting plane, rather than to a normal one in this case, okay? D is the interplate spacing, okay? We looked at the line reflect from this family of planes, okay? They are in phase when it is shining in, and they are out of phase outside. If you want to see them, they should be in phase too. But the question is, they have path difference. Okay, these two lines, when larger than this one, there's 2 green lines. Okay, to have a constructive interference in the beam diffracted in the direction theta form the entire family of planes. This one. The rays from the separation planes must reinforce each other. In other words, the distance difference, 2d sine theta, must be integral number of wavelengths, so they can be in phase too. Okay, look at this. This is perpendicular, this perpendicular. So this angle equal to this angle, and this, the green line is equal to d sine theta. You have 2d sine theta is a path difference between these two. Okay. It must be equal to m lambda, so it can be constructive interference. The H length A0 of a unit cell can be related to the interplane space D of the family of planes. Well, it's complicated. I'm not going to do it here. Okay. Regardless of the angle at which X-rays enter a crystal, there's always a family of planes from which they can be said to be reflected, so that we can apply Bragg's law. X-ray diffraction is a powerful tool for studying both X-ray spectra and the arrangement of the atoms in crystals. To study spectral, a particular set of crystal planes having a known spacing d is chosen. Diffraction from these planes diffracts different wavelengths at different angles. I detect them that can discriminate one angle from another can be used to determine the wavelengths of radiation reaching it. On the other hand, we can study the crystal itself using a monochromatic X-ray beam, determine not only the spacing of the various crystal planes, but also the structure of the unit cell. This is Bragg, okay? He won Nobel Prize in Physics in 1915. The DNA molecules and many other equal complex structures have been mapped by X-rays diffraction method. Welcome you make a comment and give suggestions. so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on College of Physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Rayleigh. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks, God.